Now let's move on to the another dimensionality reduction method, which is t-distributed stochastic neighbor embedding, t-SNE, t-distributed stochastic neighbor uh, embedding. So t-distributed stochastic neighbor embedding, t-SNE, is a dimensionality reduction technique that is commonly used for visualizing high dimensional data in a lower dimensional space. It was proposed by Lawrence van der Maten and Jeffrey Hinton in 2008. So let's look into the definition and explanation first. t-SNE, or t-distributed stochastic neighbor embedding method, is a nonlinear dimensionality reduction technique that aims to preserve the local structure of the data in the lower dimensional space. It works by minimizing the divergence between two probability distributions, a distribution that measures pairwise similarities in the original high dimensional space and a distribution that measures pairwise similarities in the lower dimensional space. Then let's look into the history of t-distributed stochastic neighbor embedding. So t-SNE was introduced by introduced introduced as an improvement over the dimensionality reduction methods, so such as PCA and LLE, which often struggle to preserve the local structure of the data. So t-SNE, or t-distributed stochastic neighbor embedding, has gained a popularity in the field of machine learning and data visualization due to its ability to create visually appealing and informative plots. So now let's look into some of the assumptions which are connected with t-distributed stochastic neighbor embedding. So t-SNE makes the assumption that the data points that are close to each other in the high dimensional space should also be close to each other in the lower dimensional space. However, t-SNE does not assume any specific distribution of the data. So that's the good aspect of t-distributed SNE, t-SNE method. So let's look into the applicability and respective use cases. t-SNE is particularly useful when visualizing high dimensional data in a 2D or 3D space. It is commonly used in exploratory data analysis, pattern recognition, and clustering tasks. So it's also popular for visualizing embeddings learned by deep learning models. So, now let's look into the mathematical equations which are involved in t-distributed stochastic neighbor embedding. So the objective of t-SNE is to minimize the Kullback-Leibler divergence between two probability distributions P and Q that represent pairwise similarities in the original high dimensional space and the lower dimensional space respectively. The KL, or Kullback-Leibler divergence, is defined as the following. So the cost function of t-SNE is now defined as following. So KL, that's a Kullback-Leibler of p sub I, given that q sub I is equal to double summation of ij to n and p sub ij multiplied by log of p sub ij divided by q sub ij. So where uh, p sub ij is the pairwise similarity between data points I and j in the original space, and q sub ij is the pairwise similarity between their lower dimensional counterparts in the embedded space. So now let's deep dive into the math part of t-distributed stochastic neighbor embedding, t-SNE. So here, to address the crowding problem and make SNE more robust to outliers, t-SNE was introduced compared to SNE. So t-SNE has two main changes. One is a symmetrized version of the SNE cost function with simpler gradients, and two, a student t-distribution rather than a Gaussian to compute the similarity in the low dimensional space to alleviate the crowding problem. So now let's deep dive into the mathematical equation or mathematical part of t-SNE. So notice that in SNE, that is a stochastic neighbor embedding, p sub ij is not necessarily equal to uh, p sub ji, because tau sub ij is not necessarily equal to tau sub ji. So this makes SNE prone to outliers, because an outlier x sub I would have very small p sub ji for all other points, and so it is embedded location becomes irrelevant. So thus in t-SNE, that is t-distributed stochastic neighbor embedding, in t-SNE, p sub ij is defined instead as p sub ij is equal to p sub j given I plus p sub I given j is divided by 2n. In this way, a summation of j p sub ij greater than 1 divided by 2n for all data points x sub I. As a result, each x sub I makes a significant contribution to the cost function, and that also gives a simpler gradient as shown later. So moreover, t-SNE uses students t-distribution instead of the Gaussian to define q. So q sub ig is, this is how we calculate q sub ij, that you can see on the screen, because it uses students t distribution, not Gaussian distribution, Gaussian g distribution. So now it's time to calculate the cost function of t-SNE. So this can be defined as C is equal to summation of KL of P sub I, given that Q sub I. And the remaining part we have seen earlier. It's p sub ij multiplied by log of p sub ig divided by q sub ij. And so p sub ij, this is how we calculate, and q sub ij, it's obviously related to the student's t distribution, and this is the cost function now. But there doesn't end the matter. So the heavy tails of the normal student t kernel allow similar, or kernel allow dissimilar input objects x sub I and x sub j to be modeled by low dimensional counterparts y sub I and y sub j. So that are far apart, because q sub ij would be large for two embedded points that are far apart. And since q is what to be learned, the outlier problem does not exist for low dimension. Now it's time to apply gradient of the cost function. So this is what we do. So the gradient of the cost function is can be calculated by dc divided by dy sub I, and to the derivative to the respective cost function, and what you get is 4 of f attraction plus reflection. So these are the two components which will be left. So where this part z is equal to uh, y sub l minus y sub s whole square whole square, the deviation can be found as t-SNE Papers appendix. So notice that there is an exaggeration parameter alpha greater than 1 in the t-SNE algorithm, which is used as a coefficient for p sub ij. So this encourages the algorithm to focus on modeling large p sub ij by large amount fairly large Q sub ij. So a natural result is to perform a tightly separated clusters in the map, and thus makes it easier for the clusters to move around relative to each other in order to find an optimal global organization. So now let's move ahead. The next thing is now let's look into the algorithm working procedure. So t-SNE, t-distributed stochastic neighbor embedding algorithm can be summarized in following 5 steps. The first one is to compute the pairwise similarities, that's p sub I comma j between all the data points in the high dimensional space. So this is usually done using a Gaussian kernel or student's t-distribution. Then initialize the lower dimensional representations of the data points randomly. Then define the similarity distribution Q that represents the pairwise similarities between the lower dimensional data points. Then we can use gradient descent to minimize the KL divergence between P and Q, adjusting the lower dimensional representations of the data points iteratively, and then repeat the step 4 until the convergence happens. So now let's also look into some of the real life examples where it actually can be applied. So t-SNE is commonly used in various domains such as visualizing high dimensional gene expression data in genomics research. Then we have analyzing word embeddings in natural language processing tasks. Then visualizing high dimensional features learned by deep learning neural networks in computer vision tasks. Then understanding the consumer preferences and clustering products based on user behavior in e-commerce. So t-SNE provides powerful visualization capabilities that help researchers and data scientists uh, gain insights into complex and high dimensional data sets, making it a valuable tool in exploratory data analysis and data visualization tasks. However, it should be noted that the t-SNE is computationally expensive and may not always preserve global structure in the lower dimensional space, especially when the original data contains a large intra-class variations. As such, it is recommended to use t-SNE as a tool for exploratory data analysis and visualization rather than a method for feature engineering in supervised machine learning tasks.